Hi guys, Dr. J here, and in this video we're going to go through a very simple example of Kriging using Python, and specifically we'll be using a particular Python package called PyKrige. So we can do this in Google Colab just by pip installing PyKrige. We can run this command. Notice that you'll need this exclamation point here when you do this command. So that will allow us to install this in the Google Colab environment. We can import the packages that we need then. And as I said, we're going to use ordinary Kriging for this. There are other Kriging modules in the PyKrige package, so you can check that out. But for now, we're just going to use ordinary. And then we'll need our observations. And we're going to use a toy reservoir problem where we've got some well locations and there's measured porosity at each of those locations. So I'm going to run each one of these cells. Let's just look at our observations here. So here is porosity is the color. And then, of course, x and y is the location in space. So what we're going to do is we'll set up an ordinary Kriging object here. And this object, I can highlight this. This is from the PyKrige package. It's going to take our x, y space variables, and then z is going to be the values that we're going to interpolate. There's different variogram models that we can pass. And you can see here from these options that pop up all the different things that you can pass. So, for example, you can specify what the variogram parameters are. You can give it a variogram function. You can specify the number of lags. So what this is going to do is this function, ordinary Kriging, is actually doing two steps in one. So whereas before we've sort of separated out the variogram analysis from the Kriging part, this ordinary Kriging function is going to do them both in one. So it's going to either estimate or use a variogram model that you give it, and then use that variogram model to do the Kriging. So here's our x and y values. Here's our porosity values. We're going to use an exponential variogram model for this case, and we'll go ahead and plot all of these things. So let's run this cell. Looks like there was some anisotropy found, and that makes sense because if we look at this plot, you can kind of see more similarity in this direction than in the cross direction in terms of the porosity values that we have. Here is our variogram. Now, of course, for this particular data set, your variogram is not going to be particularly well constrained if you were to try to fit this. Because of the fact that we only have a few observations. We only have a few, 1, 2, 3, 4, 5, 6 data points here. So yeah, not a lot of constraints on the variogram itself, but whatever we have looks like it's doing a reasonable job with the data that we have, so we'll go ahead and go with that. If we were to choose a different variogram model, a Gaussian model or a linear model, that's probably going to have a big impact on our interpolated field, just because there's so little constraints, there's so little data compared to the amount of area that we're interpolating. But we've got our variogram model now, and so now once we have the variogram model, we can of course do Kriging. And this is going to be using the ordinary Kriging equations. We've talked about those in other videos. What we need to do first is set up a grid. So you can see here I've set up a grid of x and y. And in this case, I'm just going over the domain that I'm showing here in the graph from -300 to 300 in the x direction, and from 0 to 600 in the y direction. And then what we're going to do is pass the grid, and you can see how I've specified this. This is just a vector of x values, the vector of y values. So we'll pass those two vectors using this grid keyword to the ordinary Kriging object and using this execute method. So this is now not a dictionary or an array. It's a method, a function that is sort of built into this object, and it allows us to pass a grid, in this case given by grid x and grid y. And then what we're going to get is our estimate. So you can see I am calling this z star. That's our estimates at our grid locations. So it's going to take in this grid x and grid y, calculate what the interpolated values from Kriging are, z star, and then there's this ss variable, which is just the uncertainty. So let's go ahead and run this cell. And we can look at what z star and ss look like. Turns out they're NumPy arrays, and they're exactly the size of our grid. So if we look here, grid x, and I can actually add a code cell here, grid x.shape, and then grid y.shape. So grid x and grid y are just vectors that are 60 elements long, and they go, as I said, from -300 to 300, 0 to 600. And so now our output, our z star, is going to be found on that grid. Okay, so here is our Krigging result now. So first of all, you can see that was very easy. We ran a few lines of code here, defined a ordinary Kriging object, and now we're able to get a Krigging result. So you can see we've got porosity estimate on this grid over our whole domain. The black dots that you can see are the locations of the data, as shown right here. So I'm plotting my original X and Y data. You can see that each well is giving us information not just about that particular location, but also in some region around that well. So areas with high porosity values, there's some decay of porosity, some smooth decay of porosity away and towards the areas of low porosity values. Now, this is of course only one particular model, and we'll look at some examples of other models here in a second. Now we can also compare this to what the original data was like, and I'm just going to replace here the black dots with the actual colors of the original porosity value. So if we run this now, you'll see, if we look carefully, we might be able to see the original data points there, but you can see that the Krigging is basically giving us a very good estimate of what those original observations were. It's fitting the data very well. All right, so let's go ahead and look at our uncertainty now. So with our Krigging estimate, so here's our best estimate from Krigging, we also have uncertainty, and Krigging is very nice in that it gives us the uncertainty. It tells us how uncertain our estimate is. And we can get this from this image, and this is, again, we've talked about how to calculate this using the Krigging equations. For now, the thing to notice, and that I'll point out, is that basically the uncertainty is equal to the CIL. So our CIL here, or I should say the square root, because this is standard deviation. So the CIL from our variogram model is going to be equal to the variance. So if we were to take the square of this image, and actually I've taken the square root here, so if we were to take that away, you would see what is the CIL from our variogram. And we can just verify that that is the case by coming back up here. Our variogram CIL is about 20. And let's just compare here for a second. Let me take away this square root. And there we go. So we can see away from our observations, our maximum uncertainty is approximately 20, which is the CIL value. So what that's telling us is that our maximum uncertainty doesn't keep getting larger as we get farther away from the data. It flattens out, and it flattens out at the overall CIL value, which is equal to the variance of the data. So we can get an estimate of our uncertainty here. You can see the uncertainty is lower around the data points. That makes sense. And then we can look at the model parameters for, in this case, an exponential model, as I said before, and we could begin to do some more in-depth analysis at this point. And some of that in-depth analysis might include looking at different types of variogram models and seeing how those affect the results. So let's come back up here for a second. This is pretty easy to do now that we've got this set up. Let's look at a Gaussian model. We can run the variogram analysis again. We can look at our parameters, and we execute the ordinary Krigging on the grid. That's finished, and we can print out our results and plot the results. Now here we're still fitting the observations, so you can see I'm still using the original phi values. Let me change that back to black dots so that we can just see where the data is for a second. So we still have our data in these different locations. We're fitting the data quite well, but you can see the estimated porosity is now very different. And the difference is coming entirely from the different variogram model that we use. The only thing that we've changed is the variogram model itself, and now we're getting some slightly different estimate of porosity. And basically what you see is that this estimate is smoother. So we had an estimate before which was slightly rougher. This estimate is slightly smoother. If we run the uncertainty plot now, we'll see the same thing, where now, because the estimate is smoother, we're assuming a Gaussian model, which results in smoother fields. The uncertainty is also less at farther distances from the data points, because there's the assumption built into this Gaussian model that your field is smoother than an exponential model. Well, for one thing that it's telling us is that the variogram model that we choose and the model parameters of that variogram model are going to have a big impact on our estimate, both our estimate and our uncertainty using Krigging. So those two things, our estimate and our uncertainty, are going to really be strongly tied to what our choice of variogram model is, and then of course what the parameters are that we use for that variogram model. Let's do one more example with a linear model. So linear is an even different type of variogram model that one can use. You can see here that in this case, this is basically just a straight horizontal line. It's basically saying There's no spatial correlation in this data. We just have a nugget given by this large value. Now if we run our model, our prediction is now the same everywhere, essentially. You can see some grid cells very close to the data might be a little bit different, but basically everywhere else is just the same, and it's going to be equal to the average porosity, 23.9, so basically 24% porosity. We come back down here. You can see that basically every point in our field has an estimated porosity of just under 24%. So that's just our average. Why is that the case? Well, we've told, because of the variogram model that we used, we basically told the algorithm that we don't have any spatial continuity in this data set. So if we have white noise, any individual points, no matter how close you are to this observation, could be very different. So basically we don't have any information on a point even if it's very, very close to the estimation location. Our estimate everywhere just defaults to the average porosity. If we look at the uncertainty, we'll see that reflected as well. We basically have no information now from our data. The value of the standard deviation everywhere in the field is just equal to the standard deviation of. So 3 different variogram models. So pretty important thing to be very careful with your spatial correlation model, your variogram model, and try to do the best job that you can fitting that or determining what those parameters are with the data that you have, using auxiliary data or whatever you can use to try to do a good job with that, because that's really going to impact your Krigging results. The good news is, though, that we can do this pretty easily in Python using this PyKrige package. Just as you see here, a few lines of code. I'll make this notebook available in the notes, and I'll see you in the next video.